cosmic rays near Earth. Please.
Thank you very much. And thank you for the organizers for giving us the opportunity to present this topic, which at least we find very interesting. And thank you also for the good food. It's really been great. So if we talk about cosmic rays, at least at our energies at Earth, we're usually talking about four different populations. The galactic cosmic rays, I think most people here to some extent work with galactic cosmic rays or are familiar with it, the solar energetic particles. But there's also two different populations or other low energy species, the Jovian electrons and the anomalous cosmic rays. And what I want to do in this presentation is to focus on these two populations. There have been a number of talks covering the galactic cosmic rays, and there will still be a number of talks, and I think there has been and will also be a number of talks talking about solar energetic particles. So in this sense, I'm covering the lowest energy levels. The electrons, we're talking about MEV type electrons from, let's say, 1 to a couple of tens of mega electron volt. And for the anomalous cosmic rays, from 1 to maybe 100 MeV per nucleon. Okay, so I've divided it into two, and I think I've tried to summarize some of the most recent observations coupled with modeling that should give some of the highlights, and also I've tried to use the examples that should also be useful for other people. So you could also apply it maybe to astrophysical systems. So Jovian electrons, it's basically what the name says. It's electrons accelerated by the Jovian magnetosphere. We've been measuring it since the 1970s. At Earth, it's characterized by, if you do the flux or the count rate of these MEV electrons, it's characterized by a 13-month periodicity in the count rate, and it's pretty stable from, in this case, from 1970s to 2000s. And the 13-month periodicity is expected because that's the orbital period of Jupiter as measured from Earth, so the synodic period of Jupiter. So it was expected that should be Jovian electrons, but this was confirmed when the Pioneer 10 spacecraft did the Jupiter flyby in the 1970s. So you can see at 5 astronomical units distance, there's a nice peak where it entered the Jovian magnetosphere. Why are these particles interesting from a modeling point of view? They are really interesting because they trace out the magnetic field structure in the inner heliosphere. So in these simulations, this is just one example. The sun is in the center. The left panel shows the projection onto the ecliptic plane, so looking from the top. The Jovian magnetosphere assumed in the model is over there at the blue cross, and this dashed curve is the nominal Parker magnetic field that in this case connects the sun to Jupiter. And as you can see, the intensities are high along the field. There are, of course, spatial gradients in there. But it's relatively high along the field, and there's a very large gradient perpendicular to the field. And this is because we think if you look at charged particles propagating in a turbulent plasma, which this is a nice case of, you have much more efficient transport along the field, where you have only pitch angle diffusion and then weak diffusion across the field. So you get this three-dimensional spiral structure. You can also do a cut in the meridional plane, so looking at the side-on view. So you have the sun in the middle, there's Jupiter, and you have these particles propagating to the other side of the sun due to this spiral structure. And this is really nice because you have different processes that you can probe with these particles. So this is an example of the solution method we use. That's why there's so much noise. Oh, that's the wrong one, this one. That's why there's so much noise in the solution. We use a Monte Carlo type equation or solver to solve it. And also as output of the model, we can get these, it's not particle trajectories, we can maybe say realizations of the ensemble realizations of the distribution function. Or you can even think of it as the guiding center of the particles, and you can see how they propagate for different magnetic connectivities. So in both cases, that second dot over there is Jupiter. There's Jupiter. And we look at two different observers. The first one is magnetically relatively well connected to Jupiter. The case on the left is badly connected, and you can see how the particles reach this observer much easier by moving along the field, while if you need to reach the second observer, you need to decouple from the mean field and you have to propagate perpendicular to the field. That's a very slow process, so these particles spend a lot of time propagating. Not a lot of them reach the observer, and if they do, they reach the observer with a lot less energy, so you have lower intensities for bad magnetic connection and higher intensities for good magnetic connection. We think we understand this, at least from a modeling point of view. The question is how to observe this, and usually we do our best to get the model going. We only have one data set to compare with. If you have all these uncertainties and you have this essentially three-dimensional structure, it's difficult to pin down the physics just with a single observer. Recently, however, we can do something, I think, very interesting that we haven't been able to do before, and that's by looking at the fleet of spacecraft we currently have in the inner heliosphere. So again, this is just a contour plot of the Jovian intensity shifted around a little bit. And if I zoom into this box, there's all these different trajectories. These are trajectories of spacecraft in 2021, last year, that may have the ability to measure Jovian electron intensities. So for instance, the blue is the trajectory of Mars in this case. So the MAVEN spacecraft orbits Mars. So there's in principle a data point that can measure this part of the distribution. At Earth, we have instruments closer to the sun. You have Parker Solar Probe spacecraft. This is this red trajectory that reaches very close to the sun. The orange is Solar Orbiter. There's Bepi Colombo, there's Stereo A. It's the first time we have this very extensive constellation of spacecraft measuring the particles at the same time at different longitudes, so at different longitudinal positions, but also at different radial positions. And we think we have the opportunity now to reconstruct this Jovian intensity, and by doing that we should get a lot of information about what exactly the transport processes are. If we do have this, we can extrapolate that then to higher energies and also bigger systems, hopefully. So if we've started doing this, this is a preliminary graph. If this was an AMS graph, there would be like some preliminary text in red. Where we've started to collate the raw count rates of the different spacecraft. Some spacecraft measure the Jovian signal pretty easily. Some we might have to see if we can do something about the instrumental background. From bottom to top, it's Mars, Earth position, Stereo A, no, that's Bepi Colombo, Stereo A, Solar Orbiter, Parker Solar Probe. These lines with the error bar or the uncertainty is the model solution, so what we expect from the different spacecraft. And then we've started plotting the data over it. The data is not clean, so there's a couple of these peaks in the data. These are solar energetic particle events. They still have to be taken out. But for some spacecraft, we already see a very nice trend. So recently published for Parker Solar Probe, the blue data points show these periodic little intensity jumps, which we can show nicely are from Jupiter. The same for Solar Orbiter, you can see this nice trend. The same for Stereo A. So we still have to maybe massage the data a little bit to see if we can get a clearer signal out, but in principle, we can now do these two-dimensional reconstructions of the particle intensity, which I think is really, really great. Yeah, and what makes it interesting, at Earth, of course, you have this 13-month periodicity. This is this modeled purple curve. But if you have a spacecraft like Parker Solar Probe, that's really a lot faster. You don't have to wait 13 months to complete a period. It's more like 110 days between periods. So you have also much more data being scanned. So this is really a nice opportunity and shows what we can do in the inner heliosphere at the moment with these multi-spacecraft missions. The anomalous cosmic rays, that has a much longer backstory to explain where they come from and to convince you they are actually real. These are observations, again, from the 1970s when the anomalous component was observed as an anomalous enhancement in the galactic cosmic ray intensity. So the energy spectra here, for instance, these black dots over here at higher energies show the spectrum measured at Earth for galactic cosmic ray oxygen. It looks more or less as expected. There's also protons, helium, carbon, and nitrogen. And what they saw is below 100 mega electron volt per nucleon. For some of the species, you have this increase or anomalous increase at lower energies. Moreover, if you look at this anomalous increase, this second population has a different charge state. So where the galactic cosmic rays are fully ionized, these anomalous particles are usually singly ionized. So there's an anomalous charge state as well. And it took a while to figure out where these particles come from. We have a nice or good idea at the moment. It's kind of a long story. It starts with interstellar neutral matter, say neutral oxygen, which is not affected by the magnetic field. These neutral particles enter the heliosphere. There they can be ionized by a bunch of different processes, charge exchange, photoionization, all these processes. When they get ionized, they start feeling the magnetic field, so they have to be picked up by the magnetic field. We call these pickup ions, and these pickup ions might at some point manage to reach the termination shock, which is a relatively strong structure in the heliosphere. So it's a normal MHD shock, the compression ratio a little bit above 2, medium strength shock, and these pickup ions can then be accelerated at the shock through diffusive shock acceleration. So the anomalous cosmic rays, there's a lot of physics in their creation, formation, acceleration, and transport, but they give us a way to probe the diffusive shock acceleration mechanism. So that's the paradigm before Voyager crossed the termination shock. When the Voyager spacecraft crossed the termination shock back in 2005-ish, it didn't go exactly as expected. There's observations from the Voyager crossing of the shock. Again, you see the galactic cosmic ray component at the higher energies. At the very low energies, you see particles locally accelerated at the termination shock. They were called at that point termination shock particles. But the intermediate energies were not well described by a power law, at least at the shock. And as the spacecraft moved away from the shock, it kind of evolved again more towards what we would expect for diffusive shock acceleration, some kind of power law that coincided with the shock compression ratio. However, there's a couple of different ways to explain why this happens. The most reasonable, I think, and widely accepted idea is simply that the shock is not a perfect sphere, circle. The shock acceleration is not equally efficient everywhere at the shock. And by some arguments of connection time, you can argue that the shock is more efficient at accelerating particles to the flanks of the heliosphere and maybe more inefficient at accelerating the pickup ions at the nose. So if you have such a shock that is not a continuous source of particles, they get accelerated to high energies at the flanks and they propagate towards the nose where Voyager crossed, which kind of explains this whole modulated spectrum we observed. So it's always important if you have a shock, it's not usually uniform, it's not the same acceleration efficiency everywhere. So do we know shock acceleration produces the anomalous cosmic rays? We think so, but there are different ways in which we can probe this. And the one way, which is very indirect way of doing this, is by looking at what happened in 2009. So all the previous solar cycles from 1960 up to 1990 were more or less of the same strength. The particle intensities always recovered to more or less the same magnitudes, except in 2009. In 2009, we had an anomalous increase in the galactic cosmic ray intensities at Earth. We had record-setting intensities measured by both spacecraft and neutron monitors on the ground. And I think in general, at the energies of about 100 mega electron volt per nucleon, the intensity was about 20% higher than expected. It has been studied for a while why this is the case, but it seems like as if recent solar cycles, so from 2009 up to present, are for some reason a lot more quiet than the previous or early solar cycles, which is probably due to the sun going into a much quieter phase. However, the much quieter sun influences the particles by producing less turbulence. If you have less turbulence, you have less scattering, and the particle intensities change accordingly. So there's the data. The light curves are what we would have expected, or the early solar cycles. The filled curves are the recent solar cycles, and you can see there's an excess. If you do the ratio of about 20% for the galactic cosmic rays. Now, if you go to the anomalous cosmic rays, the picture looks very different. So for instance, looking at oxygen, if you look at the galactic cosmic ray part at high energies, we see the same 20% excess in the particle intensities. But if you look at the lower energies, so this is where the anomalous cosmic rays dominate, there the ratio changes to below 1. So while the galactic cosmic rays have these super high intensities, the anomalous cosmic rays are something like 10% lower than the previous solar cycle. So the question is how to explain something like this. And we've done a lot of work, well, we're busy doing a lot of work trying to simulate this for different scenarios. This is again something we can do now for the first time, at least according to me, because we have enough spacecraft observation to remove a lot of uncertainty. So we start by simulating galactic cosmic ray intensities. For that, you need to know what the spectrum is outside the heliosphere. We have a very good idea of this at the moment because we have these black data points. That's measurements by Voyager spacecraft outside of the heliosphere. At high energies, you have AMS and Pamela observations, which constrains this input boundary condition at the highest and at the lowest energies. So you're more or less constrained what you can feed into the model. At Earth, we also have a lot of data at the moment. So we have here data for 2 different solar cycles with different polarities from different instruments, from ACE at 1 AU, also a lot of measurements from the Parker Solar Probe spacecraft. And by having all these multiple data sets, you can really constrain the model as well. So we get these curves, which is the best fit setup for the model. So you can essentially fix the model parameters with all the recent observations. Then you can see what you need to do to move between the early cycles and the new cycles and what was the difference. So this is again still work in progress. What we find is for the reference solution, this is the curve I showed just now, we get this red curve, which is, at least for us, seems appropriate for these quiet recent solar cycles. If you want to model the older or the earlier cycles, you need to reduce your diffusion coefficient. So you need to implicitly assume less turbulence. You can also couple that reduction to observations of the turbulence. If you analyze the magnetic field data, there seems to be some kind of consistency, some fraction you have to reduce it by. And what you see is this, I think, very interesting result is that if you have less turbulence, the galactic cosmic ray intensities are generally more. So the red curve, that makes sense because there's less scattering. The particles very easily propagate from the outside the heliosphere to Earth. When you have more turbulence, it makes sense. The intensities drop at Earth because you have more turbulence, more particle wave interactions, and more scattering. You get lower intensities. However, if you look at the anomalous cosmic rays, it's not so clear. You have the increase happening over here. The question is why, and is it consistent with the observations? Sure, it's consistent with the observations. There's our modeled ratio and the ratio from the data, and it seems to make sense. Why is this the case? Well, this seems to be something that pops out from the diffusive shock acceleration process. So usually if you have less turbulence, you have less scattering and less efficient shock acceleration. So if you want to have shock acceleration, you always need to trap the particles there for some time, which is not the case if you have these quiet conditions. So I think it makes sense, and it again points to shock acceleration, or it makes sense in the shock acceleration paradigm. But everything is not understood. There's a lot of uncertainty still. One of the big problems we have at the moment is if you look at the radial gradient of these particles measured as a function of distance, the model gives this dashed curve, which compares well with the older observations, but does not reproduce the newer observations very close to the sun. So there's something we don't understand happening very close to the sun. One reason might be that the cosmic ray distributions are not isotropic. So there's some mirroring happening very close to the sun, and we need to account for this. So at the moment, we're working on trying to understand this. So if you reverse our models, so if you start with an isotropic distribution at Earth, which is a magnetic distance 1.2 AU from the sun, and you evolve this isotropic distribution towards the sun, what will happen to it? Well, we have very big magnetic field gradient close to the sun, so you will have a mirroring effect, and only some particles well, you'll get a loss cone distribution, and only some particles might make it back to the sun. So if you're at 0.1 AU, this red arrow, only this very few particles in a very narrow cone can actually reach the sun, which possibly also has some observations for Fermi observations of high energy gamma rays produced by cosmic rays at the sun as well. However, when you add diffusion, and there's also always a little bit of diffusion, it looks completely different. The red distribution changes from that little beamed distribution to something that looks much more isotropic, and we are yet to look at all the parameter space. So there's still some uncertainties in the transport. But with the new observations very close to the sun, and we can actually do this for the first time and actually test if our Parker transport equation is actually valid everywhere in the heliosphere. So that's already the summary. If you're doing cosmic ray physics in the heliosphere, I think the astronomers, astrophysicists feel the same at the moment. It's really a very good time to do this kind of analysis. We have a lot of spacecraft observations and very unique spacecraft observations that we are not going to get at least in the next 50 years. The Voyager spacecraft is outside the heliosphere. That gives us a data point in which we can constrain a lot of uncertainties. Inside the heliosphere, we have Parker Solar Probe and Solar Orbiter, getting really very close to the sun, and Solar Orbiter at some point will also go off ecliptic, so you'll scan a little bit to maybe the polar regions. And at Earth, we have this very high precision AMS2 and previously Pomela data, and combining these observations in some way, I hope I showed this for some examples, can really give a lot of information of how these particles propagate in the heliosphere, which is interesting in itself. It can also be used then to model the galactic cosmic rays. But the interesting thing as well is the lessons we learn in the heliosphere can also be extrapolated then to larger astrophysical systems where you don't have the in situ observations. That's also part of the idea. And I think with that, I'm finished. Thank you.